Right now, entire countries are racing to redesign their cities, coastlines, and energy systems, not to stop climate change, but to survive it, because the climate has already crossed the point where politics matter less than engineering. For decades, climate change has been discussed as an environmental problem, a political debate, or a future risk, yet today it is increasingly experienced as an engineering crisis unfolding in real time. Floods are overwhelming cities that were never designed to hold that much water. Heatwaves are pushing urban systems beyond their thermal limits. Coastlines are retreating faster than planning cycles can adapt. In response, countries are no longer asking whether climate change is real or who is responsible. They are asking a far more practical question: how do we keep societies functioning as the climate becomes fundamentally less predictable? Across the world, a quiet transformation is underway. Nations are no longer treating climate adaptation as a secondary policy issue. They are redesigning infrastructure itself, using engineering as the primary tool to absorb, redirect, and survive environmental stress. This is not about symbolism or small-scale sustainability. It is about megaprojects, automation, and systems built to operate under conditions that previous generations never had to confront. One of the clearest expressions of this shift can be seen in how countries are responding to flooding. Rising sea levels, stronger storms, and heavier rainfall have turned water into the most immediate threat facing urban civilization. Traditional defenses, designed for historical averages, are failing. As a result, flood control is no longer a matter of local drainage upgrades. It has become a national engineering priority. In China, large-scale flood management has evolved into a systems-level strategy. River basins are treated as integrated machines rather than natural features. Massive dams, retention zones, and diversion channels are coordinated with sensor networks and automated gates that regulate flow in real time. Entire cities are being redesigned as sponge cities, where streets, parks, and buildings absorb water rather than resist it. The goal is not to eliminate flooding entirely, but to control where and how water moves when it arrives in overwhelming volumes. In Europe, flood engineering reflects a different philosophy shaped by dense populations and centuries-old cities. Rather than relying solely on massive barriers, many countries focus on layered defenses. Coastal regions combine sea walls, surge barriers, and restored wetlands to dissipate energy before water reaches urban centers. Rivers are given space to overflow into designated floodplains rather than being constrained by rigid channels. This approach accepts that flooding will occur, but aims to prevent it from becoming catastrophic. The United States faces its own version of the same challenge, spread across a vast and diverse geography. Coastal cities contend with rising seas, while inland regions experience extreme rainfall and river flooding. Engineering responses increasingly emphasize resilience rather than permanence. Levees are reinforced but paired with controlled overflow zones. Critical infrastructure is elevated or relocated. In some cases, entire neighborhoods are redesigned or abandoned as part of managed retreat, a concept that was once politically unthinkable but is now part of serious planning discussions. Heat presents a different, but equally destabilizing threat. Unlike floods, extreme heat does not destroy infrastructure in dramatic moments. It degrades systems slowly, pushing power grids, water supplies, and human health toward failure. As temperatures rise, cities become heat traps, storing thermal energy that turns urban environments into sustained stress zones. To counter this, countries are investing in city-scale cooling strategies that treat temperature as an engineering variable rather than a weather condition. Urban design is being rethought to reduce heat absorption through reflective materials, shaded corridors, and vegetation networks that cool air through evaporation. District cooling systems, common in parts of Europe and Asia, distribute chilled water across entire neighborhoods, reducing reliance on individual air conditioning units that strain power grids. In China and the Middle East, city cooling has become a strategic necessity. Dense megacities cannot function if outdoor temperatures regularly exceed human tolerance. Engineering solutions integrate cooling into building design, transportation infrastructure, and public spaces. Sensors monitor heat accumulation, while automated systems adjust ventilation and shading dynamically. These are not lifestyle improvements. They are survival mechanisms for urban life in a warming climate. Energy infrastructure is also being redesigned under climate pressure. Renewable power is often framed as a solution to emissions, but it is increasingly valued for resilience. Distributed energy systems reduce dependence on centralized plants vulnerable to heat, storms, or flooding. Large-scale solar and wind installations are paired with energy storage and automated grid management to maintain stability under volatile conditions. In China, green megaprojects are tightly integrated with industrial planning. Renewable energy zones are built at continental scale, connected by ultra-high voltage transmission lines that move power efficiently across long distances. This infrastructure is designed not only to reduce emissions, but to stabilize energy supply as climate stress increases. Europe follows a similar logic, though constrained by geography and regulation, focusing on grid interconnection and cross-border coordination to balance supply and demand under changing conditions. The United States approaches climate engineering through a combination of federal investment and regional experimentation. Coastal resilience projects, wildfire mitigation systems, and grid hardening initiatives reflect a growing recognition that climate instability is now a core national security concern. While political consensus remains fragmented, the engineering response continues to expand, driven by economic risk rather than ideology. What unites these efforts is a shift in mindset. Climate change is no longer treated as a distant scenario to be avoided. It is treated as a permanent operating condition. Engineering is used not to restore the past, but to make the future livable despite uncertainty. This shift also reveals the limits of technology. Megaprojects can redirect rivers, cool cities, and shield coastlines, but they cannot eliminate risk entirely. Every intervention introduces trade-offs. Seawalls protect one area while increasing risk elsewhere. Cooling systems consume energy and water. Green infrastructure requires land and long-term maintenance. Engineering the climate is not about winning a battle. It is about managing losses in a controlled way. For societies, this reality is both unsettling and clarifying. Climate anxiety thrives on the perception that nothing is being done, that collapse is inevitable. In reality, vast amounts of effort, capital, and intelligence are being deployed to keep systems functioning. The question is no longer whether adaptation is possible, but how quickly it can scale and who benefits from it. The countries investing most aggressively in climate engineering are not doing so out of optimism. They are responding to pressure. Economic stability, political legitimacy, and social order increasingly depend on infrastructure that can withstand environmental stress. Engineering becomes a form of governance, translating abstract climate models into physical systems that people can live with. As climate volatility accelerates, the importance of these projects will only increase. Flood defenses will be tested beyond their original parameters. Cooling systems will become essential rather than optional. Energy grids will need to absorb shocks that were once considered rare. The success of nations will depend less on preventing climate change and more on how intelligently they adapt to it. Ultimately, the story of climate collapse is not only a story of loss. It is a story of engineering under pressure. Of societies choosing to respond with design rather than denial. Of infrastructure evolving from static systems into adaptive machines. The future will not be decided by whether the climate changes, because it already has. It will be decided by which countries can engineer their way through instability, and which ones discover too late that resilience cannot be built overnight. This is the new frontier of climate engineering, where survival is no longer an abstract concept, but a measurable outcome shaped by concrete, steel, algorithms, and long-term planning. And in this world, the line between environmental policy and industrial strategy has all but disappeared.